This is the third lecture on structures. The topics will be metal structures and load on structures. In the previous lectures, we discussed the aircraft structures used in the first decades of the 20th century. Typical elements of those structures were trusses made of wires, tubes or bars, the use of linen for the skin, and wood used as material for wings. As you can see in the table, from the 1930s, aluminium entered the aircraft industry. I will tell about it in a few moments. After the Second World War, the jet engine was introduced in civil aviation, which enabled airlines to fly long distances. These flights are performed at high altitudes, which required pressure cabins. After the 1970s, the importance of composites increased. First as material for secondary structures, but today as material for primary structures like wings and fuselages, as we see in the Boeing 787 and the Airbus A350. The transition from aluminium to composites is comparable to the transition which took place in the 1930s. Douglas and Boeing were among the first aircraft manufacturers who made all-metal aircraft. In this picture you see the DC-3, a very famous aircraft which flew for the first time in 1935. Its predecessor, the DC-1 and DC-2, were all metal aircraft too, though they were less famous. The structure of this aircraft and the skin were made of an aluminium alloy. Aluminium as structural material was rather new in those days. The structures were joined using rivets, just as in steel bridges and ships. The rivets had round protruding heads and were not very efficient from aerodynamic point of view. Later, countersunk rivets were introduced, resulting in smooth outer surfaces. The fact that aluminium was rather new also shows in this picture. If you look at the skin surface, you see a lot of waviness. Also, the rivet pitches are remarkable. Sometimes the rivets are very close to each other, sometimes the rivet pitch is very large. This indicates the difficulty the manufacturers had to find good and sufficient designers and craftsmen. As you remember, for the wooden aircraft, that was not a problem. There were many carpenters available. The large variation in the rivet pattern was not a big problem, since the number of flights was limited and there was no pressure cabin yet. If you compare the previous slide with this one, you see that the quality of the metal structures has improved tremendously. This picture shows very nicely the structure of a small aircraft fuselage. You see the skin, the circular beam element named the frames, the longitudinal profiles named stringers, etc. A structure like this we call a shell structure or a semi-monocoque structure. The skin is part of that structure, so it carries also loads and it protects. This is in contrast to the linen or textile skins we were using in the early periods of flight. Note that a true monocoque has only a skin, which takes up all the loads. A perfect example of that is a bird egg. Despite the fact that the skin is carrying loads, not all structural components participate evenly in the load distribution. Therefore, we distinguish between primary and secondary structures. The primary structures carries the main load. Damage or failure of an element of this part of the structure could cause a catastrophe. The elements of the primary structure are called PSEs, which mean principal structural elements. They need to be inspected regularly during the operation of an aircraft. The secondary structures take much smaller loads. They protect, are used for access of compartments, etc. Examples of such components are hatches and fairings for aerodynamic reasons. Think about the fairing between the wing and the fuselage. Elements of the secondary structure are named non-principal structural elements. This picture shows the structure of a small aircraft. You can see the fuselage structure with frames and stringers, and the wing box with spars and ribs. All these elements work together in load carrying and protection of payload and systems. When a load is applied at the tip of the wing, the structure should transfer this load to the virtual center of gravity of the plane to make equilibrium with other forces. Therefore, the structure should provide a load path. In this case, first the load is transferred via the rib to the main spar. Next, the main spar transfers the load to the center of the aircraft. One may ask, is there a maximum limit to the applied forces? To answer this question, we look at the following diagram. In this figure, the load factor n is given as a function of the velocity of the aircraft, the airspeed. The diagram shows a so-called flight envelope. The aircraft should perform all its maneuvers within this box. The boundaries of the flight envelope are determined by speed limits and by load limits. The load factor is defined as the ratio of lift over weight. In a steady horizontal flight, for example cruise flight, the ratio is 1. See the horizontal dotted line in the figure. If the aircraft makes a maneuver by pulling up or by making a turn, the lift will be larger than the weight, and the ratio will be larger than 1. However, there is a limit to these maneuvers. They should not be too severe. How severe? That depends on the strength of the structure, so on the design. For example, a fighter aircraft will have much higher limits than a civil aircraft. This load diagram also brings me to the definitions of the limit and ultimate loads. In most cases, an aircraft operates close to the load factor 1. Only in very few occasions, its performance comes close to the limits of the envelope. The static design of a structure or a component is based on the limit loads. A high load occurring only once in the lifetime of the aircraft. All other loads in the lifetime of the aircraft are not as high. When the limit load occurs, there should be no remaining damage or deformation in the structure. When the limit load is multiplied by a safety factor, usually in the order of 1.5 or 2, we get the so-called ultimate load. A structure should sustain this load at least for 3 seconds before it fails. If it does not fail, it may have damages or deformations. The load diagram and the definitions can also be related to the different materials used in aircraft. If we look at the force displacement curve of a metal alloy, then we can see that the material shows elastic and plastic behavior. Up to the yield stress, the material behaves elastic and all deformations are reversible. Beyond the yield point, the material becomes plastic and the deformations are permanent, irreversible. If you compare the definitions of limit and ultimate load with the metal behavior, then we can state that the limit load should be below the yield point and that the ultimate load should be below the maximum load. For composites, which are elastic until failure, we can state that the ultimate load should be below the failure load. Currently, the safety factors used for composites are higher than for metal alloys, since the fracture loads of composites show more scatter. Summarizing, in this lecture we briefly discussed some features of metal structures and discussed some aspects of the forces acting on aircraft structures. Next time, the last lecture on structures will be about fatigue.